good morning, afternoon, evening, whatever it is for you. Thank you all for coming. So I'm Curious George in Second Life, Djorgovski at Caltech, and this will be first official Scientia public lecture. So today I thought I'll tell you a little more about an important development about 100 years ago, when we first realized how big the universe is and that it's expanding and all manner of other things. How did this happen? What does it mean? And what happened since then? Although not much about that, because a lot happened since then. So first, I'll tell you about how we discovered that galaxies are galaxies and not just some fuzzy nebulae inside the Milky Way. How the expansion of the universe was discovered, and what does it mean that it follows directly from the Einstein's general theory of relativity. And I'll show you at the end some of the results from deep past that we can see thanks to the expanding universe that are seen with James Webb Space Telescope. So, ever since the discovery of the telescope in the early 17th century, from Galileo onwards, people looked at skies through telescopes and noticed that in addition to a couple fuzzy patches that were known before, such as Andromeda Nebula, there are a lot more of those fuzzy patches around, between stars as it were, and they wondered what they were. Now, they had no way of finding out actually what's going on, but there was a lot of speculation, and some of the thinkers of the time thought that those may be distant equivalents of the Milky Way galaxy in which we live. And I'll show you here an image from a book by Thomas Wright in 1750, which I just love, where he kind of shows what these galaxies or nebulae or island universes are. I just love the way this is done, although they don't look like that today. And that has inspired many others, including the famous philosopher Immanuel Kant, who wrote in his book Universal Natural History and Theory of the Heavens that these are indeed island universes. And since they had no scientific way of actually proving it one way or the other, that was just a pure speculation. So it was not clear whether these fuzzy patches were island universes or just some fuzz inside the Milky Way, which was to be the entire universe. Now, things started changing around the turn of the last century, where George Ellery Hale, who's a famous astronomer and scientist and leader, first, who was at the University of Chicago, persuaded Charles Yerkes, who got wealthy by building the Chicago Elevated Railway, to build him an observatory called Yerkes Observatory nearby in Wisconsin, Williams Bay. And at the time, that was the finest observatory in the world. I forget the diameter of the refracting telescope they had. And the timing Hale had was great. Shortly after that happened, Yerkes went bankrupt. But it didn't take very long for Hale to realize that Wisconsin is not the greatest place to do astronomy from the ground. And so he went exploring in the American West and Southwest for a better site, which he found here in Pasadena, Mount Wilson, which is a mountain just overlooking the San Gabriel Valley where Pasadena is. And it was a very wise choice. Because the seeing conditions, the turbulence of the atmosphere, were excellent. And also, at that time, Los Angeles was much, much smaller, so the issue of the light pollution really wasn't there. Since Yerkes was bankrupt, he then persuaded another wealthy person, Andrew Carnegie, who's a major philanthropist, to build him a better observatory on Mount Wilson, which they did, opened in 1904. Hale actually did a whole lot of other stuff. He, among other things, started Caltech, National Science Council, started the Astrophysical Journal, etc., etc. But the observatory, which wasn't named after him, kind of named after Carnegie, but it was really known as the Mount Wilson Observatory, quickly became the leading observatory in the world. At that point, they switched from old refracting telescopes, like spyglasses, into reflecting telescopes where curved mirrors are used instead of lenses. And at first, they built a 60-inch diameter telescope, and then that was followed by a 100-inch diameter telescope, which was the largest in the world at the time. This is what it looks like, and still looks like this today. And you will notice interesting construction. The old telescopes have the solid tube lenses on both ends, but reflecting telescopes have mirrors. They just need to be held in place, and instead of a tube, they had this open construction, which was then repeated in building Palomar 200-inch telescope. And the reason for this is that lets the whole structure cool, the air can flow through, and that helps with what we call seeing, which is turbulence inside the dome itself. Well, the observatory quickly became very well known due to its discoveries. But in the meantime, something else important happened. In 1912, astronomer Henrietta Leavitt at Harvard College Observatory, she was studying pulsating variable stars, Cepheids. Some stars vary, and some of them pulsate, actually get bigger and smaller, a little hotter, a little cooler. And it turns out that for most of those, there is a great correlation between period and the luminosity of the star. That was what Henrietta Leavitt's discovery was. She was looking at the Magellanic Clouds, which are our nearest dwarf galaxy satellites. And so basically all stars in them are at the same distance, because the separation between stars in that little dwarf galaxy is much smaller than distance to them. And so you can think of it, they're really all at the same place. So you don't have to worry about differences in the distance, and then relative brightness of one Cepheid to another reflects directly their absolute luminosity differences. So Henrietta found that there is this correlation. The more luminous ones have longer period, and now it's called the Leavitt relation. And that was extremely important, and it's used to the present day because it connects two quantities, one of which depends on the distance, which is luminosity. You have to know how far a star is, inverse square law. And the other one that doesn't depend on luminosity, which is the period. It doesn't matter how far it is, it's going to pulsate with the same period. So that means that if you calibrate this relationship and you measure period of a variable star, you can just read off its absolute luminosity. You can measure its apparent brightness. From those two, you can deduce how far it is. So we call those the distance indicator relations. And this particular relation for Cepheids is used to the present day to measure the expansion rate of the universe, the Hubble constant. That enabled all manner of interesting work to follow. First, Harold Shapley, who was at first at Mount Wilson Observatory, then at Harvard College Observatory, looked at these pulsating variables in globular star clusters. Now, there was a little bit of confusion because the variables he saw in globular clusters are not exactly the same as Cepheids, but nevertheless, the picture is kind of principle is the same. And Shapley found out they all seem to be concentrated around some point in the Milky Way in particular direction, and from the relative distances of clusters, he figured out where is that center, which he then correctly interpreted as the center of the Milky Way. It was about 30,000 light years away from the sun, which was about 10 times further away than people thought. The diameter of Milky Way, it's 100,000 light years, again, 10 times bigger than what they thought then. The reason why they didn't realize that earlier is there is a dust between stars in space, cosmic smog, if you will. And so we can't really see all the way through the Milky Way. We can pretty much see stars within a few thousand light years from the Earth at most. And essentially, it looked like sun is more or less in the middle of the system because we're just some disk and kind of goes a couple thousand light years in each direction. That's it. It was actually until 1930s when people realized that there is this interstellar extinction due to the dust and able to correct for that. But anyhow, Shapley correctly figured this one out, and that with one stroke, using Leavitt's equation, the relation, he basically expanded the size of the known Milky Way or known universe at the time by a factor of 10. Still, this didn't really resolve the issue of whether those fuzzy nebulae are extragalactic, different galaxies just like Milky Way, or just some nebulae inside Milky Way, because there are nebulae inside Milky Way, star-forming regions and supernova remnants and planetary nebulae. And so why not these others? Well, there was a debate among the astronomers at the time, and there was a famous debate organized by Smithsonian Institution in Washington, D.C. in 1920, where Shapley, who at the time was really the most famous astronomer in America, thanks in part to his measurement of the size of Milky Way, debated Heber Curtis, who was director of Lick Observatory in California. Shapley thought Milky Way is the entire universe. That's what it is. But Curtis and other astronomers thought maybe not. And the reason they thought so was that they noticed novae, erupting stars, which do exist in the Milky Way. They suddenly get very bright and then fade away. And they saw exactly the same kind of thing in Andromeda Nebula and some other nearby spiral nebulae. Now, they didn't know at the time why novae do what they do. And so they couldn't really tell whether that's the same phenomenon or it's just something that kind of behaves the same way, but much less luminous. So they debated this with scientific arguments and data at the time, and it was sort of undecided who won. Now, in the meantime, George Ellery Hale kept hiring brilliant young astronomers, including this fellow here, Edwin Hubble, and they were doing cutting-edge work at the time. In particular, Hubble was charged in looking at brighter spiral nebulae, and he was interested in using Cepheids to check their distance, but it wasn't very easy to do because they're very far away, so that'd be hard to detect. But nevertheless, with the biggest telescope in the world then at his disposal, the Mount Wilson 100-inch, he kept observing Andromeda Nebula and others. And at one point, well, almost exactly 101 years ago, he took a picture of Andromeda Nebula. This is a modern picture that looks a lot better than what Hubble could do. But you can see that it's resolved in a lot of little stars. And anyway, almost 101 years ago, Hubble obtained this photographic plate. This is a negative, obviously. You can see that his picture of Andromeda is a lot less detailed than the one that I've just shown you. And he noticed that one star, labeled there with var exclamation mark, seemed to be changing brightness relative to the previous pictures he took. And this was the first time that a variable star, Cepheid no less, was actually found clearly in an external galaxy other than Magellanic Clouds. That instantly then told him that Andromeda Nebula is about a million light years away. That's only like a factor 2 or 3 off from what we know today. But nevertheless, that was much further out than the size of the Milky Way galaxy as measured earlier by Shapley. And therefore, Andromeda Nebula was outside the Milky Way, and therefore all the other spiral nebulae are also probably outside the Milky Way. So that was the second important discovery, that first Shapley increased the size of the known, quote, universe, that is the Milky Way, by a factor of 10, and then suddenly Hubble figured out it's actually much, much bigger than that, because they saw that a lot of these fuzzy spiral nebulae out there, most of them much dimmer than Andromeda and therefore probably much further out. And so that increased the size of the known universe by some huge factor. And that's what made Hubble famous for the first time. Anyhow, that was our knowledge that both Shapley and Hubble ended up on the cover of the Time magazine. And to my knowledge, only two other astronomers received that honor. One was Martin Schmidt in 1963 for the discovery of quasars, and another one was Carl Sagan. All right, the next important step in this was the discovery of the expansion of the universe. So first, Hubble figured out about 100 years ago that the universe is actually much bigger than people thought, but he was still believed at that time, early 20s, that the universe is stationary. There is no change in expansion, contraction, anything like that. But then he kept getting more distances to other spiral nebulae using Cepheids, all of them relatively nearby by the present-day standards. And he used their velocities, which were measured not by Hubble, but by other astronomers, notably Vesto, Melvin, Slipher at Lowell Observatory in Arizona. Slipher already had an inkling the more distant ones seemed to be moving away from us faster, but that was not yet well established. What Hubble, with his distances and using Slipher's velocities, plotted here is, well, velocity of the nebula relative to us, measured from the spectrum, and distance that he inferred from other means. And look, there is a correlation. Namely, that velocity is proportional to the distance, and the constant of proportionality is what we call the Hubble constant. And roughly speaking, today it's known to be about 70 kilometers per second worth of velocity for each megaparsec of distance. So the galaxy is 10 megaparsecs from us, it will be moving away at 700 kilometers per second, and so on. And we call this the Hubble diagram, and it plays a major role in cosmology to the present day. Now, since these galaxies are all over the sky in different directions, and they all obey the same relationship of velocity moving away from us is proportional to the distance, that implies that the entire universe is expanding. And let me explain why this is. Well, first let me show you a quick picture. This is what Hubble diagram looks like today. And these are for supernova explosions in different distant galaxies. And you compare that nice small scatter, well filled in compared to the Hubble's diagram. Hubble's sample is like way down in the lower left corner of this. So we now observe, use Hubble diagram to distances of many gigaparsecs, and it's a major cosmological tool. In fact, played a key role in the discovery of the dark energy. But here is why this implies uniform expansion in all directions. Now you look at the diagram at the left. So say we're galaxy A, and we look at galaxies, which could be in different directions, but just looking at their distance. And the red arrows indicate velocity vector. And find out that those that are further out move faster away from us. But now let's change the point of view. How does it look from galaxy B? From galaxy B, it looks like galaxy A is moving in the other direction by exact same velocity, and then the same amount of velocity is subtracted from galaxy C and D. So from galaxy B, they also see that galaxies are moving away from them at speeds proportional to the distance. And since the universe seems to be same in all directions, which is called as a cosmological principle, and you can think of it as sort of a version of Copernican principle, That means that indeed, from every point in the universe today, it would seem to be expanding according to Hubble's law in all directions. This is an interesting thing to note, however. You know that historically people thought the Earth is the center of the universe and everything orbits around the Earth. The Copernican revolution was that no, the Sun was really in the center of the solar system, and Earth was dethroned from being the center of the universe. So this was kind of the next step. Not just the Earth, but Milky Way is not the center of the universe or the entire universe. Or any other galaxy can claim to be the center of the universe because it looks the same everywhere. All right, so some obvious questions arise. First of all, expansion relative to what? Because if everything was expanding, then you wouldn't be able to tell. So here's an important point. There are actually two different kinds of coordinates. There are coordinates called proper coordinates, coordinates that you know and love, you can measure with rulers or whatever, and most things on planet Earth do not partake in expansion. They are fixed in these proper coordinates, rulers, rocks, the whole planet Earth, in fact, solar system or the entire Milky Way galaxy. And physically, it is objects or systems that are bound by some force. On Earth, things like rocks or rulers, they're bound by atomic forces. In space, gravity is the only relevant force, and so anything that's bound together by gravity stays same size. However, things that are not bound together by some force, like gravitational force, stay at fixed distances in these so-called co-moving coordinates. You can think of it as an invisible coordinate grid painted on space. And so galaxies are just taking a ride on those coordinates. The space expands, and that manifests itself as galaxies moving away from each other. And you can figure out yourself that then if they're all expanding uniformly, then the further away they are, they'll seem to be moving faster away from us, in a way proportional to the distance. So the space expands and carries galaxies with it. But things that are already bound by gravity or electrostatic forces or what have you do not participate in the expansion. This is how we can find out. The second obvious question is, what's the universe expanding into? Well, into itself in a way. Or you can think of it, time as the fourth dimension is in which the universe is expanding. So let me give you two-dimensional analogies. You look at the surface of a sphere. You can be expanding the radius of the sphere in 3D, but say the sphere is populated by two-dimensional creatures and they don't know about the third dimension. So radius increases in time, or if you will, radius will be proxy for time. And therefore the distances will be expanding relative to each other. That's so-called positive curvature universe. An alternative is, first, if you look at traditional Euclidean geometry, flat space, and now look at the two-dimensional equivalent thereof. Think of it an infinite plane with graph paper grid on it. So that that whole thing can be stretching in all directions uniformly, and it will be just like expanding space. So in either case, there is no edge to that two-dimensional universe. And there is no center because every point is as good as any other one. Now, expand it to three-dimensional space in four-dimensional space-time, and that's basically what we see. Now, there is a little commentary about what's outside the universe, because people at first asked us from time immemorial if the universe, where's the edge? What's outside? And theory of relativity tells us there isn't, but this philosopher can figure it out that, yeah, there's absolutely nothing outside the room in which the fishbowl is, because what can possibly be outside the fishbowl? However, it's also one more thing is important. There are other things than just distances between galaxies that expand with the expanding space. Namely, any waves, like electromagnetic waves or gravitational waves, also expand with the expanding space. And a more formal statement of this is that particles that do not have mass, but they can still have energy, expand with the expanding space. Photons, which can be of radio, light, gamma rays, it doesn't matter. As the space expands, their wavelength stretches in exactly same amount. And so if you look at photons coming from large distance, they were stretched by the expansion of the universe between the time they left and the time they arrive here. And since the wavelength is being increased, that's movement towards the red, and that's why we call the red shift. Now that's an equivalent of a Newtonian phenomenon you probably know called the Doppler shift. And that's usually illustrated by, say, approaching and preceding ambulance, that from a source of sound that's moving towards you, it's kind of squishing the sound waves, and they have higher frequency, higher pitch. When it's moving away from you, it stretches them away, and they have lower pitch. Well, the same thing applies to electromagnetic radiation. In fact, this is how radars work, or laser ranging, and so on. But on a greater universal scale, you see the same thing. And due to the consistency arguments, that amount is same, or the wavelength stretch is the same, that will correspond to Doppler shift from a galaxy moving away from us with the apparent velocity due to the Hubble law. It's not quite the same velocity, because velocities we're talking about are usually product of some kind of acceleration, but these velocities, pseudo velocity, they're due to expansion of the space, but nevertheless the measurement is exactly the same. Good. So since wavelengths of photons coming from atoms and ions and whatnot have always fixed wavelength in their rest frame from which they're emitted due to the atomic physics, and we can measure that in the lab on planet Earth, when we compare wavelength of photons arriving, say due to hydrogen or something like that, compared to what it's like in the lab, we can measure the amount of stretching that happened. And since more stretching results from larger path in space, a larger time of propagation, we can use that as a proxy for the distance. And so what we call redshift, which is cosmological version of the Doppler shift, is used to measure distances to different galaxies. And that has actually a lot of important uses. Now, why does this happen? Why does space expand? Well, now Einstein's theory of relativity. In 1905, he published so-called special theory of relativity, which describes how physics changes in different frames of reference that are moving at a constant speed relative to each other. There is no acceleration. And that had all manner of interesting consequences, like time dilation, Lorentz contraction, mass energy equivalence. But the fundamental change in thinking there was that in Newtonian physics, space and time were just a stage, passive stage, in which the rest of physics happens. And Einstein demonstrated that no, space and time are the part of the whole thing. They're participants in all of the physics. So in 1915, he generalized this theory to all frames of reference, to not just those moving at constant speed, but accelerating speed. And he also demonstrated so-called principle of equivalence, and this famous thought experiment, if you are in an enclosed elevator on planet Earth, there is acceleration downwards. But if that elevator was somewhere in space and you didn't know that, and it's being pulled by a rocket with an accelerating speed, you'll feel exact same acceleration downwards for you. So there is no difference between what's called gravitational mass and inertial mass. What I mean by this is there is a mass that comes in Newton's equations of momentum and energy and so on, measure of inertia. And there is also a mass that comes in Newton's theory of gravity. And a priori, those need not be the same thing. But Einstein's demonstrated, yes, they are. There is no difference between acceleration that's produced by through some dynamical phenomenon and acceleration that's produced by the gravitational attraction. Now that had a whole manner of other interesting consequences, one of which is that the space itself is in general not Euclidean space that you know and love. That space can have curvature, just like a surface of a sphere has a curvature in 3D space. Well, three-dimensional space can have a curvature, and usually presence of mass or energy curves the space in that way. So the whole general theory of relativity is summed by this statement I put in red, that presence of mass and energy determines the geometry of space. The geometry of space tells matter and energy where to go. And so one observable consequence of this is that if space is curved around very massive objects, say like the sun, the light rays will not move at a straight line in Euclidean space. They will move into whatever is the shortest distance in curved space. And so it looks like the mass is bending the light paths. Well, it is actually doing that. And that is a testable prediction. This does not exist in Newtonian physics. Interestingly enough, Einstein already realized this in 1913, and he wrote to George Ellery Hale, who was a famous solar astronomer already, whether it would be possible to measure this. And Hale said no, because the sun is way too bright and we can't measure positions of stars that are close in the sky. But during a total solar eclipse, it will be possible to do that. And so in 1919, there was a total solar eclipse, and famous English astronomer, astrophysicist Eddington organized 2 expeditions, one to Brazil, one to island in the Atlantic, São Tomé and Philip. And they took pictures during the total solar eclipse where sun was against the background cluster of stars called Hyades, and compared those images taken with same telescopes 6 months later, 6 months earlier, when the sun was on the other side. And sure enough, the positions of the stars changed, and changed exactly as Einstein's theory predicted. And that now really made Einstein famous. So there is a little clip from the New York Times at the time. Lights all askew in the heavens, and men of science are agog. And finally, nobody need worry, which is very reassuring. So this is when Einstein really reached the peak of his glory. And he was not on cover of Time magazine just for being person of the year, but person of the century. And of course, he's iconic, but he did not turn that into great financial riches. Like most of scientists are kind of that way. Okay, so then he actually visited Pasadena, Caltech in 1930s, and they took him to Mount Wilson, and this is like a totally staged photograph. Here's Einstein peering through the eyepiece and Hubble behind him, puffing on his pipe, and another famous astronomer, Walter Adams, telling him what to do. Because of course you can't see expansion of the universe. You have to measure a whole bunch of velocities and distances to galaxies. but it was certainly an important achievement. Basically, since the only physical force that matters at large distances is gravity, because electric, electromagnetic, so on, and even nuclear forces and particle forces, they all cancel. Charges are well mixed, or they intrinsically don't go to large distances. At large distances in space, gravity is the only force that matters. And since general theory of relativity is theory of gravity, basically, then that becomes theory of the universe. So two things: the empirical discovery that the universe is expanding, and Einstein's general theory of relativity as theoretical explanation of what essentially form scientific basis of cosmology. Now that can be expanded a little further. I won't go into great detail, but a number of other physicists looked into this and then applied Einstein's equations to understand what will happen with the universe at large scales. At first, Dutch astronomer Willem de Sitter almost immediately obtained solution of Einstein's equations for a particular restricted type of space. Then a little later, Soviet physicist Alexander Friedman, who worked as a meteorologist, developed fully general relativity-based theory of expanding universe. And at that time, in 1922, it wasn't known yet that the universe is expanding. People didn't pay much attention, but he wrote to Einstein. Einstein helped him publish his papers in a well-known German journal. But it didn't really catch attention of the community. And then in 1927, Georges Lemaitre in Belgium, he was a Jesuit priest as well as a physicist, pretty much the exact same thing that Friedman did before him. And today we call these models Friedman-Lemaitre models. And also Lemaitre kind of run the clock backwards. Well, it's expanding. What if we can look further back in the past? Then everything must have come from a single point, which suspiciously sounded like a moment of creation. And of course, since he was a Jesuit priest there, he said, yeah, of course, right? So nobody really took this extrapolation that basically means there was a Big Bang very seriously. Well, at the time. But this is what these cosmological models look like. Don't worry, it's the only scientific diagram I'm going to show you. Essentially, on x-axis is time, and on y-axis is distance between any 2 points riding on conmoving coordinate grid. And they start from 0, and simply a Big Bang, and go further apart. Now, a couple different things can happen. If there is enough mass in the universe, then its own self-gravity will slow down the expansion and turn it around, and universe will fall upon itself in a reverse of the Big Bang called the Big Crunch. Now, the Newtonian equivalent of this is, if you, say, throw a rock in the air, it goes to some height, falls back down. But if you throw it up with, say, speed of, 10 miles per second, then it's going to escape Earth's gravity and float into the solar system. Now, if there isn't enough mass in the universe, gravity will not be able to arrest this expansion, and the universe will expand forever. Furthermore, if there is so-called cosmological constant, which maybe we'll talk about at some other time, that can accelerate this expansion, and today we think we're exactly in that kind of universe. Now, here is something that's usually a misconception I'd like to really fix. Big Bang was not an explosion. Some people sometimes assume that it was like a point in space and boom, everything went from there. No. Space itself is sort of created in this pseudo-explosion. And there is no time before that moment. Now, of course, we don't really know. But Big Bang happens everywhere at once. Space and matter are all squished together into a point and expand from there. So that initial point is called the initial singularity, and since the nature usually does not have any infinite quantities in it, we basically don't know how what really happened very, very, very early on. And in order to figure this one out, we will need quantum theory of gravity, which we do not have yet. But what we do know is that the universe must have started from a very dense, very hot initial state, and that is what we call the Big Bang. Now, Lemaitre can only speculate about this, but in 1960s, two physicists working for Bell Labs in New Jersey, Arno Penzias and Robert Wilson, discovered a microwave signal all over the sky, which we now know is essentially redshifted afterglow of the Big Bang, when the universe was filled with incandescent plasma. Well, microwave background we detect is from when the universe was about 380,000 years old. Before that, it was opaque, but still very hot. And Penzias and Wilson got Nobel Prize for this discovery, because this was pretty much a clear-cut prediction of the Big Bang theory, and it was borne out exactly. So when the photons of Big Bang started, they were like a visible light, more or less. But since then, they stretched by about a factor of 1100, and now they're microwaves, like microwaves, microwave oven. But the intensity is very, very low, so that, don't worry that it will not cook you. And we study now this microwave background, little fluctuations in it, both from the ground in space. In the lower right is a picture of European Space Agency's Planck satellite. And that tells us a great deal about early universe and models of the universe in which we live. It's I would say maybe second most important discovery after Hubble finding out the universe is expanding. All right, so today, cosmology is a science, which is like science of the universe as a whole and its major constituents, kind of has three different streams of work. The first one is really realm of physics, understanding very early universe from some quantum gravity era, the inflation, to microwave background. The second one is figuring out what cosmological model do we live in, using Hubble diagram, using microwave background, using all manner of different things. And so we now know with kind of percent level precision what are the most cosmological parameters that govern the expansion of the universe. And the third one is understanding where the major constituents of the universe, galaxies and large-scale structure, come from. And things also like big black holes that we see in centers of galaxies. Before we go into that, let's go back to redshifts, right? So expansion of space stretches their wavelengths. So the light that's emitted in, say, blue or ultraviolet, some billions of years later, may be received as visible light or infrared light. And we can measure that stretch because we know the laboratory wavelength, if you will, and we observe it some different wavelength. And ratio of 2 tells us how much universe stretched since then. And using cosmological model, we can then translate that stretching into the distance. But not only do we know how far things are by measuring redshift, but we also can figure out how long in the past it happened that the photons started their journey. So essentially, the universe has its own built-in time machine. The further in space you look, is the deeper in the past you look, because light travels at a constant speed, and so the longer it travels, it's going to be arriving from deeper in the past. So we see the galaxy, distant galaxies, as they were when the light left. When today they evolved in some fashion or another, just like Milky Way did. And so by looking further and deeper in space, we look deeper in the past. And this actually is the crucial ability to figure out the evolution of the universe and things in it. So I'll end up with just a few examples of where the frontier is now using this cosmological time machine with our latest, bestest telescope, which is James Webb Space Telescope, observing the universe in infrared in a Lagrange point behind the Earth. Now, it is a 6.5 meter diameter telescope. It doesn't have to have telescope 2 because it's in vacuum. And it actually is gold plated. Those mirrors are made out of beryllium and they're coated with gold. Most astronomical telescopes use silver or aluminum of some kind. But gold has the highest reflectance in infrared. And so it's gold plated not because NASA wants to spend money, which they do, but because it really is physically the best thing to do if you want to look at the infrared universe. And why infrared? Because we're looking far away and those photons are now in infrared. So here's a quick comparison. Hubble has a diameter a little shy of 100 inches, 2.4 meters. And Keck telescopes in Hawaii have 10-meter diameter, but they also have to contend with Earth's atmosphere. And James Webb is kind of in between. And what's amazing about this is the phenomenal precision by which these mirrors have to be polished and aligned to make kind of perfect parabola. And it's approximately 1 part in 200 million. That is quite amazing. This is, imagine that the diameter of the telescope is like size of the planet Earth, then the biggest imperfections are only like a few inches. It really is very high precision optics and also very high precision alignment of mirrors. Each of these segments is kind of separately pushed back and forth. But that wasn't good enough to have a big telescope in space. So we used a gravitational 4 optics, if you will. Remember, the gravitational field can bend light rays. So a big mass in space can act like a lens, because that's what lenses do. They bend light rays. And good gravitational lenses for this purpose are very rich clusters of galaxies, of which we know many, because they have masses something like 10 to the 15, 10 to the 16 times mass of our sun, most of which is dark matter, perfectly transparent. And so if we look in the direction of a rich cluster of galaxies, it will magnify galaxies behind it by factors maybe of several tens or so. So in addition to the James Webb, you have a kind of gravitational pre-telescope that makes it even more powerful. And this is a well-established phenomenon and it's been used in observational cosmology for a long time. So now we just started using it in space as well. Well, this was the first light image from James Webb, looking towards this foreground cluster of galaxies. And you can see that these little arcs and arclets, and those are just distorted, magnified images of more distant galaxies behind the cluster. And so by judicious choice of clusters and objects to look at, we can look all the way down to over 13 billion years in the past. This is one of the deep field images where they just observed again and again and again, added up the light. And James Webb sees things down to about 30th magnitude if you're an astronomer. And that's essentially how bright would be ordinary, say, 100-watt light bulb be bright from 20 million kilometers away. That's a lot further than the Moon, not quite as far as Mars. Yeah, it's just mind-boggling how faint these things are, and the reason we can see them is, well, we have big telescope, and it's in space without atmosphere and any of that, and we can integrate for a long time and use all kinds of other techniques and tricks. This is just a zoom in on that same picture. Like every single dot that you see, aside from the one star that has kind of rays sticking out of it, that's a galactic star. Everything else in this image is a distant galaxy, some of which coming from redshifts of 10, 12, maybe even beyond, corresponding to look-back times of 13 billion years or more. Now, how do we find these distant galaxies? This is another trick that astronomers use. On the left, you see, sort of artist impression what young galaxy could look like, gas falling in, these streamers, stars forming, very luminous, and so on. Young, massive stars, extremely luminous, they're also very hot. And so the spectra of young galaxies are expected to be very blue. Most of the energy will be coming ultraviolet. The spectrum will look like a red. So you can look for very blue faint galaxies. However, something else happens. There is a lot of hydrogen left between us and that galaxy, and hydrogen is extremely good at absorbing ultraviolet light. So you can look at the galaxy like this, the spectrum that's very blue, climbing towards the shorter wavelengths, and then boom, cuts off completely because it's absorbed completely by intergalactic hydrogen. And so if you have, say, take at least 3 different filters, one of which is blueward of this cutoff and 2 which are in unperturbed region in the spectrum, you see an object that gets bluer and bluer and then suddenly disappears in the shortest wavelengths. And that is a really good way to find the most distant galaxies. So this is indeed one of the galaxies observed by James Webb. Looks just as you'd expect. And from the position of this cutoff, we can find out how far it is. And this is one of the most distant. It was there 300 million years after Big Bang, which is just barely enough time to form stars and put it all together. And here are some pictures, these false color images of 4 different galaxies. Bluest filters on the left, reddest filters on the right. And if you go from right to left, you see it's there, and then boom, disappears. And that's exactly the consequence of what I just shown. So this is how astronomers have found all these distant galaxies. They study with James Webb, and a lot of excellent science is being done with that. Okay, so to wrap up, I'll give Hubble the last word. In 1936, he published a popular astronomy book called The Realm of the Nebulae, and these are the last 2 paragraphs in it. And I'll let you read them on your own, but I thought it's very poetic. Says that with increasing distance, our knowledge fades and fades rapidly, which is why we always wanted big telescopes. And ultimately, we'll reach this dim boundary, the utmost limits of our telescopes, and there we measure shadows, and we search for among those ghostly errors of measurements for landmarks that are scarcely more substantial. And that's pretty much what frontier of astronomy is still like today. And he said the search will continue. And not until the empirical resources are exhausted need we pass to the dreamy realms of speculation. So thank you, and with that, I'll be happy to take any questions you may have. Now, please type your questions in the local chat and precede them like this. And so we'll look for questions and I'll answer them in whatever order you type them in. Bomber Fox, you forgot to type question in caps. Okay, how did Hubble come to his constant? Well, he measured it. This is what we do today. You need to measure velocities and distances to a whole bunch of galaxies, and slope of that relation is the Hubble constant. Now, that's not an easy thing to do, and you may have heard there is a little bit of a discrepancy in different ways that we measure Hubble constant. one which follows pretty much what Hubble and his successor did using Cepheids, and the other one that comes from studies of the cosmic microwave background. And they don't agree very well. And the interesting question is there something wrong with the data that we have yet to figure out? And a lot of people working on that. Or maybe there is some new bit of physics that something changed from the time microwave background was released, when it was 380,000 years old, until today with 13.7 billion years old. And that will be very interesting too, because there'll be some new physics that we can find. All right, question. How do we know that the proper coordinates in our Newtonian systems are not expanding as well, but just very infinitesimally? Well, why would they? I mean, you would have to assume a whole different physics to introduce this extra expansion. And there is no other reason to do it. Whereas if you just assume the physics we know in that puts health object together, that seems to work fine. All of the cosmological measurements are perfectly consistent with that assumption. I mean, it has to be a coordinate system that doesn't really expand in order to be able to say that something is expanding or contracting for that matter. Well, if there are no more questions, thank you all for coming, and join our group if you want to get announcements of the future, public lectures and other events that we have. Thank you.